Today it's my pleasure to introduce you our speaker, Dr. Sten Delos. Dr. Delos is currently a postdoc research fellow at the Carnegie Observatories. He specializes in gravitational dynamics and the growth of cosmic structure, focusing on the questions like the nature of dark matter or the origin of the cosmic structure like galaxies. Dr. Delos completed his PhD at the University of North Carolina at Chapel Hill under the mentorship of Professor Eric Jack. He then advanced his research as a postdoc research fellow at the Max Planck Institute for Astrophysics before joining the Carnegie Theoretical Astrophysics Center. Dr. Delos' research uniquely targets dark matter systems, especially systems much smaller than galaxies, which retain imprints of the universe's initial conditions. By using numerical simulations and analytical models, he tried to study the structures to learn about dark matter and the early universe. So today he will tell us about the dark first structures. So please go ahead.
Thank you, Billy. So let me start with some background. So we know that there is around 5 times more dark matter than ordinary baryonic matter, and because of this, dark matter drives gravitational structure formation. What this looks like is that regions of above average density in the early universe collapse under their gravity to form hot clouds of dark matter. Now, these are hot because, unlike the ordinary baryonic matter, the dark matter has no way to shed its orbital energy. And so it cannot cool, and this is why you get these diffuse kind of halo structures instead of compact objects or disks. Now, galaxies form inside dark matter halos. Here's what that looks like for our own galaxy. This is density as a function of radius for the dark matter and the ordinary baryonic matter. And just for some reference, this is about the size of the galactic disk itself. So these dark matter halos are much more spatially extended than the galaxies. But that's not the whole story. So not all halos have galaxies. Dark matter halos form over a huge range of scales. Here's a depiction of that. So this is the large scale structure, kind of the cosmic web. You can zoom in, you'd find halos associated with galaxy clusters. You keep zooming in, you'd find halos associated with individual galaxies. But you can keep zooming in on these circles, and you'd eventually get to scales where there are no, so the baryons do not cluster, and you'd find dark matter halos that are completely dark. Also, there are subhalos inside larger halos. So this is a simulation of a Milky Way mass halo, and all these little points inside here are subhalos. Now, a simple but useful way to describe a dark matter halo is with its spherically averaged density profile. This is density as a function of radius. Generally, the way these structures look is that they're dense toward the center and less dense farther out. And also, if you look at this in a log-log scale, you find that the slope of the profile, so the density decrease is shallow at small radii and steep farther out. Actually, this kind of structure turns out to be pretty universal in the sense that you can look at in dwarf galaxy scale halos or cluster scale halos, and they have the same behavior. And this kind of universal structure is shown over a huge range of masses here. So this is not the same thing as this. This is the slope of this plot. So the d log rho by d log r. As a function of radius, and this is showing density profiles in a bunch of different mass ranges. And the key thing here is that these all overlap with the appropriate scaling. And so this is telling us that these density profiles are pretty universal.
Right, there was that from simulations. Is that from simulations?
Yes, it's exactly from this simulation.
So the halo there identify the small halos. Are they isolated or can have a more dense environment?
So these are all kind of field halos, not subhalos.
Okay.
Yeah, and that they're all in.
So in terms of numbers, that's not the major fraction of the small halos. Most of them are.
Yes, actually, that's something they had to do for this group had to do for this simulation, because you can't do this kind of successive zooming in on a region that is collapsed.
Okay, right.
I guess it's just related to the certain density profiles of halos that aren't in like the most underdense regions possible different. I know you can't go over so many decades in mass, but presumably we can still look at this in its environments.
Are they different? So they should be. Let's see. So density profiles of halos that are of the really small halos that are not in these underdense regions, they would be subhalos today. And so they would evolve like through kind of tidal evolution, but they're kind of initially they should be pretty similar.
So this is unbody only.
This is pure embodied.
So how do you know that at this smallest scales, there is no variance?
Right, so this is because it's because of the baryonic gene scale. So what happens is, okay, there are some scales where you form galaxies, where you have halos that are massive enough to accrete baryons. And so those baryons can cool and form galaxies. But once you get to smaller scales, your baryons are too hot. This happens at around like 10 to the 5 solar masses. The baryons are too hot to cluster on that scale. And so you can, they're essentially just a homogeneous background. This is just, I should point out that halo formation happens in the field outside of galaxies. And so what would happen is if you have a density excess, it is large enough that the baryons can cluster, then you're going to collapse and form a dark matter halo that has also an overdensity of baryons. Those baryons are going to form a galaxy. But if you're at a scale that's too small for the baryons to cluster, because the baryons are too hot, then you would just form a dark matter halo in a baryon background. And that dark matter halo would not have baryons in it. Does this make sense? Okay. You can see this even in like the results of cosmological perturbation theory. There's some characteristic scale where you have baryons tracking the dark matter and then they kind of cut off. Okay, so but now okay, why do halos have the density profiles that they do? Well, it turns out that these density profiles could be mostly connected to their mass accretion history. So this is the plot version of what I talked about at the dynamics meeting. This is the way you can frame this is that the mass inside regions denser than some multiple of some density. This is a density profile shown in kind of a weird way. So mass is a function of density. You can make this kind of plot, and you can also, for the same halo, make a plot of the mass as a function of time, but as our time parameter, we're going to say density of the universe. And those turn out to make almost the same plot. They're a little bit different, like shifted a little bit because of contraction of particle orbits, but they end up being really closely related. So halo density profiles are set by their growth histories.
So what sets the value of alpha?
Yeah, so this is standard virialization arguments would say that it's around 200, but then you have orbital contraction that makes it higher. So it can be up to like 1,000.
But that parameter was used somewhere to make this plot. I'm a little bit confused.
So this is purely from simulations. These are showing density profiles in some simulations from this paper. And these are mass accretion histories from simulations. And then the conclusion here is just comparing this plot to this plot. So if you look over here, they exactly match, right, at kind of the present time or the outer radius of the halo, depending on which plot you're looking
I'm
at.
just wondering if to make this plot, I'm confused how you actually make this. Is this alpha entering into this plot?
No. So that's a conclusion from here. If these
But when you made it, did you have to pick an alpha? No.
no.
So it's just why are we talking about this?
I thought that the M that you're plotting on the left-hand side plot is defined as the mass inside regions above the density. So you are using
But
alpha 200 in the left.
No, so this is mass inside regions. So here we have, I guess you could say we have alpha equals 200, but since these don't exactly match, you would conclude that alpha is something bigger than 200.
So you've chosen alpha is 200 to make this left-hand plot, but had you chosen 476, it wouldn't be much different, basically.
So what would happen is, right, so I didn't make this plot for, it's this group, right? What would happen is if you change this 200, that would shift these curves to the left, which can make this point, for example, match this point. And I think you need something like 800 for this point to match this point.
But that'll match the light blue point, but not necessarily like the star or the triangular point.
I think it matches. I think it matches all of them pretty well. Well, not quite, because there's I mean the spacing between them is pretty close. But yeah, this group comes up with some kind of relationship that is not completely constant, and it can't be, because I mean with this factor of 200, these points out here, like the outer radius matches. Okay, so I've talked about dark matter halos and how they're set by the accretion history, but now I want to think about the first systems of particle dark matter, which form without any meaningful accretion history. This is work I've done in collaboration at various times with a number of different collaborators. And then later on, I'm going to talk about an alternative dark matter picture. Okay, so let me give some context here. This is a diagram showing the main phases of cosmic structure as a function of redshift or equivalently time and mass scale. So at large masses or at early times, we have small fractional perturbations to the density of the universe. And what happens is that over time, these become gravitationally amplified and you start to get nonlinear structures. You're going to get dark matter halos. And this process happens earlier at smaller mass scales. Now, this would apply if the dark matter is arbitrarily cold and has perturbations on arbitrarily small mass scales. But now, suppose there is some scale on which the early universe was smooth, like a free streaming scale. Then I claim that there's another phase, the prompt cusps. So this story starts with the cosmological initial conditions. These are a random density field that is expanding over time and getting gravitationally amplified over time. But now I say that on some scale, on some sufficiently small scale, the initial density field should be smooth, for example, due to the thermal motion of the dark matter. And in a smooth density field, there are well-defined local maxima. And these are going to be the places where gravitational collapse begins.
But do you really need there to be a cutoff in like QP of K, or because in the regular lambda CDM, it only grows logarithmically as you go to IK. Is that good enough for all?
Not good enough. Yes, you need to have a cutoff. Okay, so here's what that looks like. What this process looks like. So we can see this is a density excess in a random field. Evolving as a function of time, you can see kind of this smooth gravitational amplification until this thing basically collapses all at once to make compact structure. And here's what that structure looks like on the inside. So this is the density profile, the density as a function of radius at different times, from earlier times before collapse to later times. And the key thing here is that this is a straight line. So it's a pure power law. And actually, if you plot density times radius to the 3/2 power, you find that it's a horizontal line. So this is a 10⁻³ density cusp. Now, the most interesting thing about this is that it stabilizes. So if you look at these kind of early times, the coefficient of this power law is set basically immediately after collapse. And so this is a prompt cusp. Now, this prompt formation is important because of what it means for the properties of these cusps. Because their properties are set immediately, they can only be sensitive to the very close neighborhood of the initial density peak. Namely, it's so you can characterize a peak by its size, its some characteristic size, co-moving size, and a collapse time. And it turns out that, so then you can write down the only relationship that is dimensionally possible, which is to say that essentially the size of the cusp is proportional to the physical size of the peak at the collapse time. And the density of the cusp is proportional to the density of the universe at the collapse time. And you get this relationship, not with the numerical coefficient. So the numerical coefficient comes from simulations. But the important thing is that it doesn't depend on cosmology. It's just set by gravitational physics.
Physically, what's the scale of like the size of this cusp relative to sort of the scales that I should be thinking about?
Yeah, so the scale of the prompt cusp is set by the smoothing scale, the free streaming scale of the dark matter, the smoothing scale in the initial conditions. So we don't know that, but that is in principle something we would want to measure. So for example, for like typical cold dark matter models, like weakly interacting massive particles, that maybe it would be around Earth mass. Physical size could be something like 1/100th of a parsec.
But so in terms of this relation, you're characterizing the peak by a height and the second derivative, some sort of curvature.
Yes, exactly. That's exactly it. Okay, so this makes predictions that match the simulation pretty well. The prediction is this black line. There's also some radius prediction that I didn't write down explicitly. And this works for other simulated cusps as well.
Why would the factor 24 not depend on some cosmology? I mean,
Sorry, what was that?
why the factor 24 could not depend on cosmology somewhere?
Because it's just a consequence of collapse of a smooth density peak. So irrespective of the cosmology, there's going to be smooth density peaks at some scale. And right, if you zoom in enough, they're going to look like quadratic.
That's fine, but the 24 is a dimensionless number. So why couldn't it depend on, let's say there was a little bit of dark energy, Hubble.
Okay. So you're thinking, so it doesn't depend on the matter power spectrum. It just doesn't depend on the statistics of the density field. You're right that it could depend on if there's some homogeneous background. Yes. Okay, now since these prompt cusps are set just by the local properties of the peaks in the initial density field, you can predict their distribution using the statistics of peaks in a Gaussian random field. And these are set by the matter power spectrum. So here's a picture of the matter power spectrum in dimensionless form. So this is essentially the squared amplitudes of typical density variations as a function of their wave number, which is an inverse length scale. And what's going to happen is that depending on your dark matter model, there is going to be some kind of cutoff in the power spectrum, and this is the smoothing scale. So for warm dark matter, this might be around like dwarf galaxy scales. For weakly interacting massive particles, maybe around Earth mass. Or you could think about even colder dark matter. And the prompt cusps are going to form at that smoothing scale. So here's what that looks like for an example dark matter model. So what this calculation looks like for some 100 GeV weakly interacting massive particle. You can just calculate analytically what the distribution of initial peaks looks like in terms of, for example, moving size and collapse time, and then just convert that into a distribution of cusps. So this model makes around Earth mass cusps with radius around 0.01 parsec. But this is just an example. You can do this for any matter power spectrum or almost any power spectrum. And so this connects again to the dark matter model, also connects to the physics of the early universe. So you could think about changing the primordial power spectrum due to inflation. Or you could think about changing post-inflationary physics and modifying the matter power spectrum that way. So I worked with a former student, now postdoc, Himanish Ganju, who characterized some of the observational consequences of early matter domination, which makes this kind of bump in the power spectrum and produces really dense prompt cusps.
One question, no, so because the power spectrum at those scales is so flat, it means that these things form, but very quickly it falls into something bigger that is collapsed. Not in your examples here,
Yes.
but in the standard thing. Does this affect, are the things going to survive very long, or maybe, yeah, they're not much denser than the thing they're falling into, this kind of question.
Yeah, so you can, this is like a backup slide I have, but you can kind of, okay, so I will say that's a difficult thing to simulate because you need to resolve the cusp and then you need to immediately resolve some really large stuff. But you can look at what you can just do the statistical calculation of what these density excesses look like. So this is density contrast as a function of radius. This is for like a standard, this log squared K power spectrum. And what happens is, okay, so we might be worried about something where you have this density peak and then you immediately also have similar density excess at much larger scales, which is going to mean that you immediately grow to a much larger size. But it turns out that most of the peaks look like this. And this is where you have this peak and then you have a little bit of time before you're growing to a much larger size. And the way to kind of understand this intuitively is that you're always going to be building up the smaller perturbations on top of the larger ones. So even though on average, you have this kind of really, how do I say it? It seems like you're immediately going from small scales to much larger scales. If you look at all the individual objects, you'll find that what happens is if you're adding this large scale perturbation to the smaller scale perturbations still typically have time. They're just going to collapse earlier.
So this is after how long?
So this is time is kind of arbitrary in this plot. So this is showing the density.
Yeah, because the fraction might change if you write it.
Yeah. I think I required like 20% or so in the scale factor, which is enough time for if we go back to those earlier plots of like prompt cusp formation. This is all happening in like 10% of the scale factor. This whole thing is forming. So like going from A collapse to like 1.1 A collapse. Oh, sorry, I jumped ahead here. So go back to this picture. Okay. Yeah.
These numbers of like 84.96%, whatever they were, 86.94. Anyway, is this also somehow related to like I guess the distribution of eigenvalues of the tidal tensor around that peak at all? Because it sort of seems similar to like the distribution of like pancakes and like filaments and halos, right? That you get from like the larger scales of the Rich type calculation.
I haven't thought about that. Yeah, I mean, this. Let's go try and find this picture again. So this calculation here has doesn't involve the tidal tensor at all. But when I'm comparing that, like, I'm not explicitly comparing this to this. I'm actually comparing the ellipsoidal collapse time because that's what says when the cusp forms. So I'm comparing ellipsoidal collapse time to the kind of spherical collapse time for all this larger scale stuff. Okay, so one more feature of prompt cusps that's actually a feature of any density cusp, which is that. Well, okay, so I said that the prompt cusps form due to smoothing of the initial conditions due to thermal motion of the dark matter. But on top of that, that thermal motion is going to affect the internal structure of the cusp. And in particular, it's going to lead to a finite density core at the center. So this is a simulation that showed this effect. What happens is that as you increase, so this is actually in a halo because they don't have a smoothing scale, or at least they don't have a smoothing scale that is appropriate to the size of the velocity dispersion in the simulation. But what they find is that as they increase the velocity dispersion of the dark matter, we have, with no velocity dispersion, we have kind of this NFW-like profile, and then you start to get a central core. Now you can predict this analytically using conservation of phase space density. What happens is that there is some maximum phase space density set in the early universe. It's roughly speaking, it's the density of the dark matter divided by its volume in velocity space. And this, if you require, or if you ask when this density would get exceeded inside the center of a density cusp at late times, this gives you a prediction for the core radius and the core density, which looks like this. So doing this a calculation explicitly for some like cold and warm dark matter models, you find that typically the prompt cusp covers about a factor of 500 in radius between the outside of the cusp and the central core. Okay, so I've talked about prompt cusp formation and how it relates to the initial density peaks, but now you might wonder if they survive. So in particular, I showed you this simulation, but what happens to this object over a much longer time period? So here's what happens. This is the same kind of density profile plot, density times radius to the 3/2 power as a function of radius, going from earlier times in purple up to later times in red. And what we see here is that actually the buildup of material there's a buildup of material at these larger radii that makes a standard halo density profile. So this is the Inasto fitting function. But at the center, to the extent that we're able to resolve it, the initial at the -3/2 cusp is still there. And this is actually not a surprising result because what happens as halos grow is that most newly accreted material has too much energy and angular momentum to sink into the center of the system. This is why it's just building up the density at larger radii. Now, you can actually deposit material and potentially disrupt the center of your system with major mergers, but that effect turns out to be small in realistic configurations. And so the outcome is that we should expect that every halo and subhalo has a central prompt cusp. Actually, this outcome nicely illustrates why I think of prompt cusps as a different phase of cosmic structure from dark matter halos, because we have this prompt cusp that is set by this monolithic collapse process. Its properties are only depend on the local properties of the initial peak. And then around it, we get a halo, which is set by the growth by this gradual accretion over time. You can actually think of it as some kind of accreted atmosphere of the initial cusp. Okay, so prompt cusps survive halo growth, but another important question is, well, I've been using the statistics of peaks, basically saying every peak can be associated with a cusp at late times, and you might wonder, to what extent is that true? Because halos are going to merge over time, or the cusps going to merge over time? So here is an estimate of the number of cusps in a simulation. So number of cusps as a function of time. Here is the prediction from just using statistics of peaks, how many peaks should have collapsed. And there's some reduction in the number of peaks that actually do collapse. And the reason for this is that a number of initial peaks are actually going to accrete onto existing structures before they can even collapse. And then beyond that, because of cusps merging together, you get a little bit more reduction in the number. But overall, around half of the collapsed peaks, it seems, can be associated with prompt cusps at late times. This depends a little bit on the matter power spectrum. There's one little detail here, which is that if you actually count the halos in the simulation, you find that there's a continuing decrease over time, count the number of bound objects, but that's a resolution artifact. Now, another interesting question is that, well, today, most prompt cusps should be substructures of much larger systems. And you could wonder, well, to what extent do they survive actually near us, meaning at our position in the galaxy? So it turns out that a significant fraction of the prompt cusps should survive. So what I'm showing here is I'm taking this dark matter model, weakly interacting massive particle, and looking at the distribution of the prompt cusps in terms of their annihilation luminosity. Well, this should be similar for other properties. So this dotted line, this is what you'd get if you don't account for any suppression of substructures. Now, if you account for the overall galactic tidal force, you would get this dashed line, so you get basically a small suppression of all cusps. And now if you account for encounters with individual stars, where these are like Earth mass cusps encountering stellar mass stars, then you essentially destroy around 2/3 of the cusps, but leave the remaining 1/3 of them essentially unaffected.
These cusps form even under self-interactions. Like if dark matter particles can annihilate, then now you have a cooling mechanism, right? And it's like extremely high density there. So
yeah, so the density at which that becomes relevant actually is a lot lower than the core density that I was mentioning before. So this ends up not being important. So another way to put that is you start making enough annihilation radiation that you would easily detect these things a long time before you make enough annihilation to, well, okay. Yeah, so right, the statement I was saying earlier depends on the cross-section. But if you make the cross-section high enough for annihilation to affect the internal structure, then it would be way too high for indirect detection. We'd already see it. Okay, and this is all based on some very nice modeling of tidal forces and the effect of stellar encounters from Jens Stucker. Okay, so I've established that prompt cusps would persist today, and now let's look at what this means for observations. So here is the matter power spectrum again for some different dark matter models, and in particular, we can think about warm dark matter, where we have the cutoff at dwarf galaxy scales. And in that case, prompt cusps of warm dark matter should affect the structures of dwarf galaxies. So the warm dark matter paradigm is that random particle motion is in the early universe is going to smooth out the initial conditions. And so this is all happening before halos form. But once halos start to form, this is what the consequence of this is going to be that you have fewer low mass halos. So that's the consequence of warm dark matter that people usually think about. But I'm going to say that, well, the initial in this smooth field, the initial density peaks are going to be much larger, and so the prompt cusps are much larger. And you could actually compare these. You could look at what prompt cusps would be predicted in nearby dwarf galaxies. So here are two examples, some classical dwarfs. The black and gray bands, these are the observationally inferred density profiles. And these lines here are predicted prompt cusps for several different warm dark matter models. This is different warm dark matter masses. So a lower mass particle is going to move faster, going to stream farther and make a larger prompt cusp.
So here, in reality, what you are computing, or maybe if not, you correct me, is what happens in a cold dark matter model with a cutoff, and putting the size of the cutoff to be the one that you might compute associated with warm dark matter. But in your simulations or anything like that, these random motions are not really.
Yes,
taking into
that's
account.
right. So I'm not actually
Should I
putting
worry about this?
Do I worry?
Should
Sorry.
I worry that some of these conclusions might not apply?
So. Yeah, okay, so I'll just comment that. Yeah, I don't explicitly put the velocity dispersion in the simulations because this would lead to discreteness noise.
Yes.
The consequence of that velocity dispersion should be this, the central core. And so for warm dark matter models, you can calculate that. It ends up being, you get a slightly smaller than 500. So 500 to 1000 is more for a cold dark matter. For warm dark matter, maybe 100 to 200. But that's not enough to affect these prompt cusps. So this is like a factor of 100, and we're not actually observationally seeing what's happening down here.
The statement of velocity dispersion would lead you to sort of have something that's still prompt cusp, now flattened out, core-like, and then transition into the normal NFW, like or cosmological.
No, so
to the cusp.
the core is at the center. So you could think of, right, you have this.
Core cusp and then NFW.
Yeah, so you'd have this NFW, and maybe the orange cusp here, and then a core over here. And yeah, the reason is there's a big separation of scales between the free streaming scale and the scales that essentially particles are moving right now due to their thermal motion. And this is because the particles actually do most of their free streaming during the radiation era. Okay, so roughly based on this picture, well, okay, so I should mention the interpretation is that if the inferred, sorry. That's the wrong button. So the interpretation here is that, well, if the inferred density profile lies above the prompt cusp, that's fine. You can just explain that with later halo growth. But if the prompt cusp is above what's measured, then that is more of a challenge to the warm dark matter model. Now, okay, so roughly speaking, this looks like you might be able to constrain 2 This is not, I didn't do any detailed constraints in this paper, but I should mention that you could do better with ultra faints, but I wanted to emphasize the broader points instead, which are that prompt cusps represent enhanced structure at the free streaming scale, which is the opposite of what people are usually thinking about for warm dark matter. And this enhancement of structure is tightly connected to the initial conditions, to the matter power spectrum. It's a signature of the free streaming scale. Okay, so next I want to talk a little bit about annihilating dark matter. So prompt cusps boost dark matter annihilation by a factor of by about an order of magnitude. And so Yeah.
Just before you switch topics, you alluded to this, so when you have a cutoff in the power spectrum, you shift the half mode mass at which the mass function becomes suppressed, and people like Ethan Nadler, for example, have set constraints on warm dark
Yeah.
matter mass from trying to infer suppression in the abundance of dwarf galaxies.
Yeah.
How competitive is having, like a statistical sample of many dwarf galaxies and trying to infer what the half mode mass constraint is versus having, very pristine observations of the inner structure of a number of dwarf galaxies and trying to infer the presence of a cusp there?
Yeah. So this, right, based on this picture, it looks like we're not quite as competitive. Only getting to like 2, 3, like maybe if you look ultra faints, maybe like 5 keV. Yeah, well, one issue is that this is here I'm predicting the kind of average cusp. But what you really want is, given some halo, what is its central cusp, and that's something that I'm working on right now. And because on average, if you have some kind of pretty dense like dwarf galaxy halo, its cusp should also be denser.
Do you get these cusps in fuzzy dark matter cosmologies?
Fuzzy dark matter. I would say I don't think so. And so you do have a smooth like smooth initial density field for fuzzy dark matter, but the first structure that you form, the first structures I think are like these soliton cores. There might be, I think that you might be able to make some kind of similar relationship where you're predicting the soliton as a function of like the initial peak, but I think you'd get a cusp. Okay, so dark matter annihilation. Annihilating dark matter is popular, and that it's basically motivated by the idea that dark matter should have been produced somehow, and why not produce it by pair production? So you have a dark matter particle with this kind of interaction with a standard model, 2 dark matter, 2 standard model. In the hot early universe, you can pair produce the dark matter or have it be in equilibrium. And this would mean, however, that at later times, you could detect annihilation radiation from the dark matter. And it's a 2-body process, so this scales strongly with the density of the dark matter, which means it would be boosted by the high density inside Prompt's cusps. And so this is a plot of something that's proportional to the average, so the annihilation rate per mass of dark matter in the cosmological average. Here's the prediction for Prompt's cusps. And it's about an order of magnitude above previous predictions from halo and subhalo models. This is as a function of redshift. So actually also one really nice thing about the Prompt's cusps is that this is a really simple prediction. It's just from the statistics of peaks and the connection between initial peaks and Prompt's cusps. Much simpler than these previous predictions, which have, some of the simpler ones are just extrapolating downward from large scales. So it's not clear how well that holds. And then you have all this, more careful models have all this semi-analytic modeling. And also these previous models all neglected that baryons are not, that dark matter is not all of the matter. Whereas here it's quite easy to account for.
So this is just the counting of peaks from Gaussian random fields and the universal shape that you have.
Yes. And then I'm taking this down by a factor of about 2 due to clustering. So you can use this to put new limits on dark matter annihilation. Basically, annihilation rate scales as the number of cusps, which scales as the total mass of dark matter. So annihilation rate from Prompt cusps, which I claim dominates the overall annihilation rate by a factor of about 10 based on this comparison. So this means the annihilation rate is basically going to scale with the total mass of dark matter, which means you want to look at the most massive systems. So here is a result from looking at the isotropic backgrounds, basically Prompt's cusps everywhere. Now that turns out to be a bit problematic because when you don't have any kind of spatial template, the astrophysical foregrounds are a problem. So you can do a little bit better by looking specifically at galaxy clusters. And we get a result that's a factor of a few stronger than the classic Fermi dwarfs limit. This is from looking at nearby dwarf galaxies. Now, I should point out that prompt cusps don't significantly boost the annihilation rate from dwarf galaxies because they're already very dense just from the smooth halo. And also because that high density means that you're going to disrupt cusps more. And it's a similar story with the galactic center, actually even more important because you have so many stars there that you'd have almost no cusps survive. Okay, just a really quick mention. Well, you could even think about really cold dark matter. In this case, because the prompt cusps survive locally, they should be passing continuously through the solar system. So I don't think there are immediate prospects for detecting that, but in principle, you could do a gravity experiment to detect those and to try to probe really cold particle dark matter. But I want to emphasize again, so I looked at the effects of different dark matter models, but this is the prompt cusps are much more general. You can use them to probe early universe physics, just anything that changes the matter power spectrum. And because of how tightly they're connected to the initial peaks, predicting the distribution of prompt cusps is just a math problem, not a physics problem. And detection of any prompt cusp. So prompt cusps measure the free streaming scale and what's happening at the free streaming scale. So detection would deliver precise information about the nature of dark matter and the physics of the early universe. Okay, so prompt cusps arise from a smooth density field. I want to quickly mention an alternative model where the initial density field is not smooth, and this is where the dark matter consists of black holes that formed in the early universe. In this case, the first structures form out of actually individual black holes. So this is work I've done with Antti Rantala, Fabian Schmidt, and Sam Young, and then also separately, if I have time, I'll mention something with Mustafa Amin. So let's consider some scenario where the dark matter is around 10 solar mass black holes that formed in the early universe. Here is, so just for comparison, a particle dark matter simulation, and then we have primordial black holes. We have early structural information because the black holes are independently distributed in the initial conditions, and so you can randomly have regions that have more black holes than others. But now, here, we account for all the really short-range dynamics. So this is just a standard cosmological simulation, the collision list one. And now we're accounting for all the short-range dynamics. So things like large angle scattering, binary formation, and even relativistic gravity.
If you take, for example, asteroid mass primordial black holes, you wouldn't see this because.
You would see this, but scale it down.
Okay.
Scale it down in mass or in size.
Relativistic gravity, you just mean like rate energy loss from gravitational wave emission, or?
So yeah, like post-Newtonian corrections, but also gravitational wave spirals. And those are pretty interesting too, because you get these relativistic recoil kicks.
You're just considering pairwise PM terms.
Yes, I think that's right. Yeah. And it's so well, okay, so the whole in the everywhere we have I think it's like first post-Newtonian order, and then the really close encounters we go up to 3.5.
But actually, if you change the black hole mass, the angle density changes, and so probably relativistic corrections become more important because the density goes high.
So I think the scaling works out because you're decreasing the masses of the black holes so much that ends up winning out. So relativistic effects become less important as you bring the mass down. Does that make sense?
I'm not convinced, but okay.
Okay. So here's a comparison between if you don't account for all the short range stuff, this is just a standard cosmological simulation with force softening, short range force softening. And then here we have all of the kind of collisional effects, short range gravity. And what happens is that the number of clusters of fewer than around 1,000 black holes is reduced by a factor of about 2. And here's an example of part of why I think this is happening. So this is a cluster of black holes. And you can see it's gradually kicking off, gradually evaporating until you're just left with a binary. And this is kind of interesting because this suppression of the abundance of black holes is a lot more than than people previously predicted from standard two-body relaxation arguments. And I think it's because a lot of this happens. So every black hole, every black hole cluster has to grow from a state of just a few particles. And at that point, you have like n-body collisions to account for, not just two-body.
Are these two-body or n-body interactions between black holes more important in the very early universe or in the later universe when things are collapsed?
So you form these binaries in the early universe because of the Poisson distribution, but their interactions with third black holes and like interactions between more than two black holes become important once you start making structures. So kind of in the later universe, although still pretty early because you're starting to make structures just a little bit after matter radiation equality.
Will that depend on the mass?
So this does not depend on the masses. So let's see, the masses enter when you start thinking about you start to think about like, so the total simulation volume here is about 10 to the 6 solar masses. But if we're thinking about what happens as you start growing to galaxy scales, then the mass matters because you have this kind of change in the matter power spectrum.
So the fact that there are black holes is not particularly relevant, just any solar mass thingy.
Yeah, so we do have relativistic gravity here, and that does matter for the black holes. You have like gravitational wave and spirals, but a lot of this is just n-body, like Newtonian n-body, consequences of Newtonian n-body with 10 solar mass things.
Sorry, the black hole mass distribution now, this just a single mass.
It's
Or
it's like a log normal, but it's pretty tightly centered around 10 solar mass.
Is there a reason to set it to be a log normal?
It's basically what you expect from some certain kinds of primordial black hole formation mechanisms.
Oh.
So another thing that's really interesting that arises in this simulation is that you change the velocity distribution of the dark matter. So the dark matter is primordial black holes. They're initially cold, but you make this component of hot black holes. Now, a lot like hot in the sense that they're moving fast. Now, this is a bit tricky because a lot of this is just binary orbit motion, and that doesn't correspond to hot dark matter because you're not actually streaming. But because through interactions with these binaries, you can actually make a component of hot dark matter. And so that's what this is showing. This is instantaneous velocity up here. Here's the average velocity over some long time interval. And you actually make this tail of really hot black holes. And you can, so here's an example. The action is going to start around here. Yeah, moving up here, we have an interaction with a binary and a single body that just kicks them both out at really high speeds from this cluster of black holes. One more time. So we can estimate what kind of mass scales should be affected by this component of hot dark matter by thinking about the gene's mass based on the streaming velocities that we calculate that we find in the simulation. And so roughly speaking, so these are 10 solar mass objects and systems scaled up to around 10 to the 10 solar mass are affected at the few percent level. Their growth rate should be affected. So the interactions between individual black holes are affecting structure on billion black hole scales.
Sorry, I'm confused about what did you actually do?
So this is right. Okay, so fraction of mass that resists clustering as a function of time, and then I'm considering different mass scales, and these are calculated by saying, okay, I have the velocity distribution in the simulation, and for each velocity, I can associate the gene's mass. And that, so because these particles are moving, they're not going to cluster on some mass scale.
Sorry, these are, yeah, I'm confused about. Yeah, confused. Can you?
So
What's happening? The
we-
black holes.
We have this velocity distribution.
You're discussing the effect of this tail. This way.
Yeah, exactly. So we have this velocity distribution. I can associate each velocity with a characteristic gene's length, like a length scale in which it would cluster, and then I can say that I can convert that to a mass scale, and that's what I'm doing here. Okay, and then let me quickly mention, because this is one of the big reasons primordial black holes are popular. They make gravitational radiation because of these binary and spirals. And here's the usual calculation. So you can calculate the time scale for a binary merger. It depends on semi-major axis and the orbital eccentricity. It actually depends really strongly on orbital eccentricity. And the idea here is that over time, this system is going to gradually radiate away energy until it merges. Now, okay, so here's the prediction. Here's what we actually find in the simulation. So no correlation whatsoever between the actual merge time and the predicted merge time. And that's just one thing. So another thing that's really interesting is you get this.
What do you mean? These are binaries that you find in this calculation.
That merge. Yeah, binaries in the simulation that ends up merging during the simulation. You can look at when they merge. When you get the binary and spiral in the simulation versus when you would have predicted it to happen when you first identified the binary.
It's not in isolation, it's binary.
Yeah. I mean that's exactly it. Yeah. But the other really interesting thing here is that there are some systems. There's this population that is not predicted to merge. Actually, this is log 10, so this is like 10 to the 10 gigayears. So you don't expect these to merge. And you can even look at them later. So this is when the system is first identified, but you can look at later and you still find that there's a population, there's always a population. Or like this population is basically always never predicted to merge, but then it does merge.
Well, that's not too surprising if the binary is very soft. Right? What I find surprising is that if the predicted merger time is very short, then it doesn't match the observed merger time, right?
So yeah, this population.
Yeah, why would that not align?
Yeah, I mean, I think it's just the perturbation. So the issue, I mean, the reason for both of these is that your time scale depends really strongly on orbital eccentricity, and it's easy to change that in interactions.
But still, the effect of perturbation should be more important for longer merger times.
Yes.
Right.
Yes.
And this is, I mean, maybe it's a bit evident from the blue population there, but it's not super evident.
That means there's a correlation between the separation of your binary and the environment density. Like if your all tight binary also happen to be located in dense region, then they're also
Okay.
impacted.
Okay, fair enough.
Yeah, so basically you can change the eccentricity with interactions fairly easily. And so you should think of, instead of thinking of binary system gradually radiating away energy until it merges, you should think of it as it has some eccentricity that's randomly jumping around, and it randomly gets really close to zero, and then you merge quickly. And this is already recognized actually by the star cluster community. Now, since we have a simulation, we don't need these analytic predictions. You can calculate what the gravitational wave energy density is in the simulation. It's, for this particular model, it's probably way too high for these LIGO Virgo Cockburn limits, but that depends on the frequency spectrum, which is something that we're planning to look at. So this is energy density in gravitational waves as a function of time. Okay, let me just mention one really quick. One thing really quick. So that was all assuming that the primordial black holes are initially cold dark matter. You could think of what happens if actually they're moving. So this is structure formation with cold primordial black holes. This is warm, initially warm. So they're initially moving like warm dark matter. And what happens is this wipes out a lot of small scale structure. It ends up being a really interesting calculation to say what the power spectrum is, because essentially what happens is you have the standard growth of the matter power spectrum at scales that are larger than the gene scale. Growth is suppressed below the gene scale, but the gene scale is getting smaller and smaller over time. It's moving to the left in this plot. This is K over here. And so these smaller scales are eventually able to grow. They just take some time. They just have to wait longer. Yeah, we have this kind of fun calculation with symbols, with diagrams here, but basically you can think of its power spectrum as a sum of the basic Poisson noise, like 1 over n. And then you have this product of two different types of perturbation that are sourced by the Poisson noise. I don't really understand why exactly it turns out that way. And that this accurately predicts the power spectrum, and also the halo, you can use it to predict the halo mass function, subject to one caveat, which is that you don't want modes that are smaller than the gene scale to contribute to nonlinear clustering, because they're too transient. Okay, so I'll just leave my summary here since I'm out of time. Thank you.
Go back to that what that Jimmy was asking about.
Which one? This?
Yeah, this one. That's why I'm also confused about why things don't converge to the. I guess the blue line is the one-to-one.
Yes.
Why they don't converge to that, but because initial predicted merger time, if that's 10 to the minus 6 gigayears. So a binary that's the thing I always remember is 30 plus 30 solar masses merges in a Hubble time if it's initially at 0.2 AU. So 10 to the minus 6 gigayears is 10 to the minus 7 Hubble times. So I'm going to need to go at least 2 orders of magnitude smaller because it scales like R to the 4. So I'm going to have to go 0.002 AU or something like that. Now, how can a binary of that separation have any interaction with its environment?
Just one thing, these actually raise eccentric, so it scales. So, you're right. Okay. Well, I fix eccentricity after. Okay.
No, so yeah, so the thing I said was for circular, but
Okay.
it's very strong.
Yeah, I mean, it's
initial. It's still, even if it's hugely eccentric, that's folded into the initial prediction. It's not going to be affected by the.
Yeah, I'm not exactly sure, but so one thing to keep in mind is that if you never had any interaction with a third body, the orbit would always be radial. You would always have zero eccentricity. And so you need the interaction with a third body in the first place to make the orbit not radial. And so all you need is that this interaction is slightly different from the simple estimate, or how would I say this?
Why would it be radial? You mean circular?
So no, radial, because if the dark matter is cold, well, you have like the Big Bang, right? Everything's moving away from everything else. Your binaries are moving directly away.
So they're formed with extremely low angular momentum.
Yes.
Extremely high eccentricity.
Yes, exactly.
So that does break this down well.
And that's if you form two in the universe, right? But there are.
Yes, exactly, and that's the issue.
I didn't understand the LIGO plot. What what is higher than the LIGO limit?
Yes, okay. So this is energy density and gravitational radiation in units of the energy density or the mass density of the dark matter, like the primordial black holes. So yeah, the blue curve is what we get in the simulation. You can do some kind of extrapolation to redshift 0 because simulation stops at redshift 5 or so. And over here I have omega gravitational wave. What fraction of the current energy density is in gravitational radiation? And this is around, depending on the extrapolation, 10 to the minus 6 to 10 to the minus 4. And the LIGO-Virgo limit is that per logarithmic frequency interval in some frequency, it should be less than 10 to the minus 8.
So this is excluded.
Probably, but this depends on some details of the frequency spectrum of gravitational radiation, which is something we're working on.
If you pick the masses of these black holes to be in the range of masses that LIGO is able to see, the radiation comes out in these frequency bands.
Yes, I think that's right. So this should be
correct for the redshift.
Yeah.
I don't know, but.
Yeah, I think the redshift is the main question.
Okay, since we are out of time, let's keep the discussion at lunch.